In the last video, we explored how to evaluate the Whisper model using word error rate or WER. We calculated WER for the dataset and found it to be quite high, around 90.4%. Today, let's fine-tune the Whisper model on our custom dataset, the air traffic controller dataset, and see if we can reduce this particular error. The first step is preparing our dataset in PyTorch format. Even though we already have the dataset, it needs some restructuring. For example, when we load the first sample, we get audio in a NumPy array and the corresponding text, also the sampling rate. For this, we create a dataset object that can handle requests for specific indices, which returns the corresponding input and the target for that index. Here the input is the log mel spectrogram and the output is the tokenized transcript. Here there is one issue is that as we take batches of input and output, for the input we have a fixed size of 30 second of log mel spectrogram. If it's less than that, we pad to that extent. But for the output, we have to do some engineering. We have to do some padding for the output as well. Right now, we see that the output has varying sizes, and that won't work because we are going to batch it using a tensor. For that, we have to have a fixed size. And in this case, I choose 60 as my transcription size. Anything larger than 60 will be truncated. Anything less than 60 will be padded. This is just to avoid issues with tensor format during the training. Now coming to our Jupyter Notebook file, first we import all the necessary libraries. And this part is especially to downsample the audio to 16,000 Hertz. Then I imported all the necessary components such as tokenizer, feature extractor, and the model itself, and then the dataset, the air traffic controller dataset. Then why did we choose the 60 tokens as the fixed length? By analyzing the transcript lengths in the dataset, I found out that most lie between 20 to 30 tokens, with few exceeding 60. To standardize the transcript, longer than 60 are truncated and the shorter ones are padded with a placeholder value of -100. After that, we convert this Hugging Face dataset into a PyTorch compatible dataset, which inherits from torch.utils.data. There, the main part to focus is this part. So here we load the sample given the corresponding index. From that sample, we get the audio data, and using this audio data, we convert it to input features, which is the log mel spectrogram. From this particular item or sample, we get the corresponding transcript, and then we convert this transcript into token format using the tokenizer. Here, one thing to note that we are padding it to maximum length, and the max length we are setting by this max length parameter. If it's more than, if any transcription is more than this max length, we'll truncate it and it will return a PyTorch tensor. In the later line, what we are doing is we are converting the padded values to -100. And then we are removing the first token because they are the labels. They do not need to predict the first token because it's already there. That's why we're removing the first token from which is the start of transcript token. And after that, we are just giving it as a dictionary, input feature and label. Once the dataset is ready, we pass it through the data loader. This organizes the data into batches, let's say with a batch size of 8 for this case, and shuffles them for beta training. Here, each batch contains the input feature and their corresponding padded label. Now comes the fun part, the training model. First of all, we initialize our device, which is the CUDA in my case. If we do not have a GPU, then we specify here CPU. Then we initialize the optimizer. I'm using Adam W optimizer, which will optimize all the model parameter with a learning rate of 1 e to the power -5. And I'm doing it for maximum 5 epochs throughout my training data. Then I'm running my training for 5 epochs, and inside each epoch, I'm iterating through the train data loader. From the train data loader, we get a batch, which is the dictionary of input features and the labels. As our model is in the GPU, we pass this input and output into the GPU as well by calling toDevice. After that, we pass it through the model, the input feature and the label to get the output. And inside the output, there is the loss attribute as well. Then we can use this loss value to backpropagate through the model and optimize the weights. In order to better visualize the training process, I added this extra codes, but they are not necessary for training. So what they're doing is they're plotting the running word error rate. So what is this word error rate? In the last video, we went detailed about it in the I. If you haven't checked that out, I put that in the I button. And in that video, we discussed how we get the word error rate from a particular dataset. And here the dataset is the validation data, which the model is not seeing during the training. All right, it gives us the corresponding word error rate in terms of percentage. And here we see the result that from the 0th to 5 epoch, the loss keeps on decreasing. If you do not remember in the last video, before training the model on the default Whisper small model, we had a word error rate of 90%. But after training for 5 epoch, we reached to a word error rate of 8.75. And that is definitely a significant improvement. Once the model is trained, it is saved using torch.save and it can be loaded anytime for inference. After that, I tested few example using this fine-tuned model, and we see here the true transcription and the predicted transcription closely resemble each other, way better than what we had before. I randomly selected 5 tokens from the validation data and just printed out their true transcript and predicted transcript. With more training, the accuracy definitely could improve even further. And yeah, that's it for this video. We fine-tuned the Whisper model using a pure PyTorch loop, diving into the details of data preprocessing, tokenization, and training. For those who are seeking a simpler approach, the Hugging Face's trainer API is a great alternative if you don't want to go to the bits of this model. In the next video, we'll tackle fine-tuning Whisper for a low-resource language. If you speak a regional language, this could help you train Whisper model for accurate transcription in your native tongue. So see you in the next video.